Okay, welcome everyone to these pre-recorded lectures on quantum topology. So the plan is I will put all the necessary links in the description. So the plan is that I will give 10 lectures, which I will pre-record online, and there will be also live lectures, which won't be recorded, which hopefully isn't a big problem because we have pre-recorded lectures. Um, so, let me share my screen. Um, so the main idea is Uppsala. So the topic of this lecture is quantum topology without topology, and I will go through my lecture notes and explain, what's basically happening. As I said, the lecture notes and everything else will be down there in the description for you to click on. And the main idea here is that I will try to explain how categorical algebra gives rise to very nice topology and representation theory. That's why I call it quantum topology without topology. So there won't be any, strictly speaking, there won't be any topology. But implicitly, we'll see it already today. Implicitly, there will be a categorical version of topology if you want. So there will be 10 lectures, and I will follow my script. And well, we basically directly dive into categories. So classical theory of categories, monodal categories, pivotal categories, braided categories, and so on. You can see here the table of contents, what I'm going to discuss in these lectures. And basically, I'm following the book in the description, EGNO, so Etting of Gilaki, Nikšić, and Ostrich, but I will give it my own flavor. So you will see I will draw much more diagrams than they do because I just like to draw diagrams. Sometimes I just can't speak. I'm sorry. So let's just dive directly into the first topic: categories. This was really bad. Categories. So what are categories? Well, we will see. So basically, so by the way, I'm really indebted to the Corona crisis. So due to Corona, as probably most of us, I just learned much more how to use kind of new technology, well, very new technology, of course, to whatever, record lectures, to do much more stuff online and so on. So there are some pretty good upshots of Corona. Maybe I shouldn't call it 2020 because it's 2021 now and we are still having a crisis. Well, oh yeah, I will probably change this in the next version, whatever. Anyway, so let's dive right directly into it. And so here's the Rosetta Stone. And if you don't know what a Rosetta Stone is, um, um, it was really the main tool to decipher the Egyptian hieroglyphs. And basically, what you can see here are the old Egyptian hieroglyphs and various two different text translations of the same text. So this is always the same text, written in a different language. And it turned out that this one was known. And so you could use this text to decipher, well, the other two. So that was the Rosetta Stone. It, it really was kind of a huge breakthrough in uh, in well the study of the history of the Egyptian hieroglyphs and whatever. So this ancient Greek, and ancient Greek was pretty much known, right? So kind of the Romans still kept the ancient Greek language. So this Rosetta Stone was discovered by Napoleon troops in 1800 something. Is not so important. Here's a link. You can click on the link if you want to know more about the stone. The point is that I will kind of follow the same outline. So there will be a language which we don't understand, and I call this language topology. And there is some intermediate language, which is quantum topology, which we kind of understand, or let's say I kind of understand. And at the bottom, this is basically algebra or category theory. And they're all the same language, right? So that's the whole point. They're all talking about the same things. They just use, well, different symbols, if you want, like on the Rosetta Stone. And I will use this part to decipher the rest. Right? So that's the whole idea. Okay, very good. So here, basically, the outline. Okay, I added a few more other things. I won't talk too much about logic. Maybe I will do this in another lecture. I won't talk too much about physics. I just have no idea about physics, but maybe I will also do this in another lecture. But basically, we want to go from here. We want to discuss how those three are related. So in category theory, you will have something that's called an object, and you will have morphisms, and you will have some other structures. And there's some equivalent things in algebra and topology. So an object, for example, in topology could be a manifold, something nice like a sphere, a torus, those things, right? Manifolds, something reasonably nice. And basically, a morphism is like a relation between your algebraic data. Right? In terms of topology, it's like a cobordism. It tells you how two manifolds are related. If you want to think in terms of physics, it's like a system, and how two systems are related is called a process. So all of this kind of have very nice relations, and they're really kind of the same language. I'm going to explain, as I said, how to go from here all the way to here, and maybe at one point I will kind of sketch what's going on here. Maybe this is worth another lecture. But well, you can see the Rosetta Stone only has three facets or three different texts, and so I can only discuss three different aspects of the theory, which is a pretty rich theory. Okay. Um, so the goal, as I said, well, let me just repeat it. The goal of this lecture is to use category theory, something many people are afraid of, but it's actually pretty easy. It's easy in the mathematical sense that there is not much structure. It's just that doesn't mean it's easy for the human mind because it's very abstract. But I will try to do my best by drawing as many pictures as possible. And in some sense, everything is kind of related to algebra, topology, physics, and logic. And you will see a lot of pictures. Okay. And at the end, everything will be centered around the quantum invariance of links, which are completely defined in the categorical language. And they arose in the 80s. Jones's discovery of the Jones polynomial was kind of the first breakthrough. The discovery of quantum groups by Drinfeld, Rashid-Tikin, and co, and so on. And there's some kind of the Witten-Rashid-Tikin derived approach, which basically says that everything, the quantum groups and not invariants, are the same in some vague way. Anyway, so the goal is to explain quantum topologies or quantum invariants of links without ever mentioning anything about topology. Right? And hopefully along the way, we will understand a little bit more about categories and why I like them. You don't need to like them, but I do. And you will see a lot of pictures. So categories are actually kind of built to have a diagrammatic description. And if something has a diagrammatic description, it's related to low dimensional topology. It might not be completely obvious, but basically since Penrose in the 70s, 60s, this is kind of a general philosophy. Everything that has a reasonable diagrammatic description is related to some low-dimensional physics and some low-dimensional topology. Okay, but we begin at the beginnings, of course. So the main thing I want to sell today is basically the slow. Classical mathematics is based on sets, and modern mathematics should be based on categories. Like sets, categories are kind of like sets, which with a slightly different formulation of logic, with a slightly different focus on what is important. And that's what I want to keep you in mind. So we certainly begin now at the beginnings, right? There are some conventions. Doesn't matter so much if you read the text, read the conventions, but I'm going to explain everything in words anyway. So for the lecture, it doesn't matter so much. So we begin at the beginning, right? As usual. So what is a category? Well, a category is strictly speaking just a collection of two things, a collection of objects, which are usually denoted by x, y. So we have some x here and some y here and some z here, and now I'm running out of letters with some a here, whatever. So they just live somewhere. It doesn't matter. Let's just say we have a collection of objects. So that's one of my conventions is that I don't care about that theoretical issues. It really doesn't matter so much. And the main point is we also have a collection of morphisms. So we don't just have like a set. A set is a collection of elements, x, y, z, a. We have something like that, but we also have a collection of relations between those things. So we have a morphism, which I usually like to draw in arrows. So here's a morphism going from A to Z, here's a morphism going from A to A. Y only has morphism going to itself. So in some sense, a category is kind of a discrete, well, it's not really, but you can think about it like as being a discrete, something like a graph, discrete object. Graph. And so a one-dimensional object, a graph. The arrows are, so these are the objects, and these things are the morphisms. Okay. And the whole point of category theory is, in contrast to set theory has elements, and all the focus is on the elements. In category theory, all the focus is on the morphisms. Morphisms are more important than objects. And you can see it, right? And for a graph, what really matters, if you think about a graph, what really matters are how things are connected and not what kind of vertices. Of course, they are not unimportant, but what really matters is how things are connected. And this is what a category works. And if you have this picture in mind, and you really just accept that you have two collections of objects and morphisms, then it makes sense to, well, to let's think just to have random objects and random morphisms. That doesn't really help. Then you can say basically nothing, right? Everything is a collection of random objects and random morphisms. So you want to have some axioms, and the axioms are basically just built what you think that should be. So this is just saying there's an identity. An identity just means if you. So what you think is you want to consider path in this graph, and the path is called a composition. And it's usually denoted with this symbol. So I can compose this arrow F with this arrow G. And now my picture gets a little bit cluttered, but anyway, and this is F composed with G. So you have a graph and you want to take path in those graph. Okay? And you kind of want to have the axiom such that taking paths, so running around this path makes sense. So the first thing you would assume is, okay, there is a very boring path, and that's a path. I stand here and I don't go anywhere. The identity path, so don't move. And this identity path is identity. It is just, well, whenever you compose it with another path, nothing changes. It's a very harmless description, and well, some people don't like non-associative things. I certainly don't, and you have some associativity action. So HGF equals HGF. So yeah, well, if you go F and then decide to go GH, it's the same as if you go FG and then you decide to go H. Yes, so those are the axioms of a category, and you always want to have a composition. That's just what the first axiom says. But these are really just built to make sense of I want to have a graph and I want to walk around that graph. Yes, and I will always just for convention, I will almost never write f composed with g. I will just write fg, and I use the usual convention, which I'm pretty sure if you're following this lecture have seen before, namely the reading convention is from right to left. So f first, and then g. And this is called the composition of G after F or F before G. This is identity. And yeah, just keep in mind that I ran endomorphisms for home from X to X. Okay. And everything is built such that end X is always a monoid. So it's kind of a group without inverse. It's not kind of a group without inverse, it is a group without inverses. It's got a monoid. Think about the natural numbers. So example of a monoid would be the natural numbers with addition. Yeah. You don't have any inverse. The natural numbers, you don't have -5, right? And the whole point is this pretty naive description, like a graph, a collection of objects, a collection of morphisms, and you walk around, generalizes quite a lot. Very familiar concepts. Well, they generalize monoids, as I said. Just read through those examples, and you should really think like, oh, my category. So this is a really nice example of a category. It just has one object, a dummy object, which I call bullet, and the homomorphisms of that object is just my monoid. Right? So I have my object here, and I have lots of arrows, and arrows are enabled by elements of my monoid, and m prime is just given as m prime, either reading in the category or reading in the monoid. So it's really naive, right? Of course, there's a category of sets. Some people would call this the prototypical example of a category. So the objects are sets. Here's a set X, here's a set Y, and my morphisms are some maps between sets, whatever. This could be the set 1, 1, 2. This could be the set 1, and YF could be the map that sends 1 to whatever, 1 and 2 to 1. Well, there are not too many options in this example, but anyway, you get the point. So a collection of objects, my objects are sets, a collection of morphisms, my morphisms are maps. And this is how you think about a category, right? A category is like a graph where you put at your object some things you like. Vector space is my favorite category ever, right? My objects are vector spaces, V, W, and I have a linear map between them. Or in more concrete terms, finite dimensional vector spaces, and after a choice of basis, F would be a matrix, right? So morphisms would be matrices, and yeah, let's check. Yeah, there is an identity matrix. Yeah, matrices are associative, and yeah, composition of matrices makes sense. So yeah, this is certainly a category. Yes. So, and there's a slightly nicer category, which I'm also going to use, which is finite dimensional vector spaces. So vector space is finite dimensional vector space, and K is just some ground field. If K, if you want, can be C. I don't really care. It's some ground field. So if you like complex numbers, it's complex numbers. If you like real numbers, it's real numbers. If you like the algebraic closure of F101, then it's the algebraic closure of F101. Very good. The one confusing point which I would like to mention is that traditionally categories are named after their objects. So set is a category of sets, but actually the main players are the morphisms. And I really want you to keep that in mind. The main players are the morphisms. Maybe I make this in a different color. The main players are really the morphisms. Okay. In the category of sets, I don't care so much about sets. I care about morphisms. There will be other categories which I will mention later, like module categories or some algebra, building groups or whatever. So everything you can basically think of. Yes, I should say this is formally not correct to think of morphisms as maps. morphisms are really more like arrows. It's really more like in a graph theoretical sense. There's no harm to think about morphisms as maps. Totally fine, totally fine. Do that if you want to. I'm always doing that. But strictly speaking, is not correct. So here's a category. It just has three objects, one, two, and three. Very good. And it is just it's a discrete category. I just have some random arrows between them, which are just named FG and the composition. And of course, and the identities which I never draw. So identities are never drawn. That's just one of the conventions. Let me just write it down. So secretly, I have the identity of one here, and so on. But they're part of the axiom data, so I don't care. They're secretly they're there, but I don't really care. Okay, so let's get rid of this. So they're never wrong. And the evident, in this case, you have the evident composition rules, right? A GF is a GF. And yeah, in this case, they're not maps. This is just completely abstract. Here's an object called 1. Here's an object called 2. Here's an object called 3. Here's a map called F. Right? It's an arrow and morphism called F. It's not really a map. But anyway, as I said, it's completely okay to think about morphism as maps. It's strictly speaking not okay, but heuristically speaking, it's almost always okay. So don't worry about it too much. And this thing is also sometimes called the commutative diagram. It just means all ways of running around the face are the same, right? If I run around FG or I run around GF, that's just the same by definition in this case. Sometimes it's not so easy to check whether something is commutative. It's sometimes called diagram chasing. So it's the art of checking whether diagrams are commutative is called diagram chasing. But in this case, it's by definition. Okay, so let's go to some really nice examples, my favorite examples, and the main examples basically of this whole lecture series. The category 1 of one-dimensional cobordisms. And the objects are really easy. The objects are just points. So let's say 3 points. That's an 3 points. Yeah, learn how to count. 4 points, 3 points, for example. Or let's say 2 points. 3 points is a bit bad in this example. Okay, so object 2 points and 4 points. And what are the morphisms? The morphisms are just all one-dimensional cobordism aka strengths, right? AKA strengths that you can draw in between them. So everything you can just take your favorite vertex and connect it to your favorite other vertex in any way you want to, and try to do it in something like that. Right? Try to do it in some generic way such that you don't have any double. Well, you could just do it, but you only want double. You don't want these triple points. You don't like triple points, right? But you can always avoid triple points. But because if you just slightly push the 120 here, that's okay. That's good. And you can draw all those pictures. And what is composition? Composition is just stacking of pictures. So if you have a picture down here, something that looks like this, and you can compose it with another picture, which might look like this is really bad, which might look like this. Then you would get a new picture by just, oops, that's not what I wanted to do. I have to get a new picture by just connecting the lines. And yes, this is now a picture from 4 to 2 bullet points. And before it was something from 4 to 2. So here's an example. And this also means I reading is in this direction from bottom to top. Very good. So this is an important example. So let me just say it once more. It's a very naive construction, The objects are just bullets, and you just put your bullets anywhere. You think of them as being aligned on a line. So here are 5 bullets. Bullet to the 5th I would also write bullet to the fifth for the obvious reason. And here's one bullet, so this is a bullet. And morphisms are basically all connection of bullets that you can draw in between. Composition is stacking things. And yes, you can have close internal components and allowing that. So you could have internal component which looks like this or whatever. This is a morphism from 0 points to 0 points, which is also perfectly allowed. So what is identity? By the way, the identity is just this diagram, right? Because up to rescaling, if you stack this diagram to anything else, you just get the same result. Okay, very naive category. Objects are points, and morphisms are strings. And this is my prototypical example of the category. You can beef this up a little bit in the category of one tangles. Well, it's exactly the same, but you now allow something like to pass. You think of them as being in three space, and the string can go underneath the other or overneath the other. Right? You can have something like this, or you can have something like this. But otherwise, it's exactly the same category. And from physics, now comes a little bit of physics. There's a category one state, which is exactly the same. I call this the category of one-dimensional states. But now you have orientations on the arrows. And what you think is like each dot is some kind of particle. And the line is how the particle travels through time and space. Right? And this is let's say this is an R3. So a particle can go underneath or something like this, right? This was hopefully right. So a particle can go over the other. Here's one particle, here's the other particle, and they cross each other in space without hitting, right? It's three-dimensional. I call this one state. And you don't need, that's the point, right? Now comes the point. You don't need to know anything about, physics or whatever, but this looks like a really nice category for physics. It's extremely naively defined. You have the same, basically the same objects. Now you would need to distinguish whether it's pointing upwards or downwards. So maybe it's better to write pluses and minuses. So this is a minus plus plus. This is something like a plus 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 minus minus. And you could just connect them according to the orientation. You stack things together, and you think of them as like tracing how particles fly through space. I'm not really sure whether I should call particles fly through space, but you get the point. How particles move in space. That's why it calls one state. And it's really still the same as this one, just with a little bit more extra data like orientations and over and under crossings. So what I really recommend is try to understand this category, and the rest is just making it a bit fancier. And in my notation, I don't use, okay, this was really bad. I should have prepared. In my notation here, instead of using pluses and minus, I use dot star and dot. So this is a minus and this is a plus, and you will see later why I actually use dot star and dot. So dot star is just meaning I have something like this from dot star to dot star, and dot is the opposite. Orientation pointing upwards, orientation pointing downwards. That's the difference. Anyway, so these are the crucial examples, and I hope at least one example makes sense to you, right? So classical examples of sets or vector spaces, some discrete examples like just a category which has, this was really bad. Just a category which has certain drawings here and there, and some arrows that it makes sense. So discrete categories. That's how I really want you to think about it. Like this is a discrete data. This is like a graph, and you can walk around edges of graphs. This is the same example, and some topologically motivated examples. Oh yeah, let's draw diagrams, right? And rules are just, How can you compose diagrams? You just stack them together. And you have to come up with some reading conventions, and my reading conventions are just from bottom to top, always, by the way, always from bottom to top, right? Why? Well, I like to build things, right? So if I want to read from top to bottom, it feels like time is flowing and I'm getting older and older and older. No. I like to build up things, right? So I read it from bottom to top. Anyway, these are the main examples. So classical categories, sets, vector spaces. Topological categories like this one, states, discrete categories, graphs. Okay, so was a big example, but this is how I usually do the lecture. I give you a definition, I try to motivate it by examples. That's how I think it should work, right? Always keep in mind that people don't come up with an abstract definition like, oh yeah, this is what I want to study. They have a real big number of examples in mind and try to find the common feature of those examples. And then they get rid of those examples, formulate an abstract definition. And then in hindsight to you and me, it looks like, oh, they came up with abstract definition in the first place, which is usually really not true. There's a huge bunch of examples people have in mind. And this is really how you should learn those category theory things. Just look at examples and then you will understand the abstract definitions, because all the abstract definitions are motivated by examples. Okay. Two more definitions, which are not super important, but anyway, well, they are of course very important, but they're not. Well, you will see. I mean, you can form, if you have a category, you can form a pair category. It's just like a tuple, right? You have a tuple of object and you have a tuple of morphisms. Everything is component wise. Nothing really exciting. So the pair category, just we will use it several times for several constructions, because now you have tuples of things. If you have a pair category, you can pair it again with itself, and you have triples of things and so on. Whatever. It's basically by construction. This is a category. And there's also something funny. It's called the opposite category. It will also appear from time to time. And it's basically saying, well, if I have a category from X to Y, who tells me what my reading convention should be? Why should I read, in this case, from X to Y? In the opposite category, so this is C. In the opposite category, it has the same objects, but all arrows are reversed. So reverse composition, right? Reverse composition. What am I doing? Holy shit. Okay. So what am I doing? So this is F, this is G, and then you would have FG in the opposite category, and you would have GF in the category. So this is in C, Z, this is in C, and this is in C op. It's just reversing all reading conventions. That's it. I mean, why does it make sense, right? So reading convention is sometimes something bad, because I have to make a choice, and whether I want to read from left to right or from right to left. Hey, you might be used to reading from left to right or from right to left, but it doesn't really make a difference, right? So there should be exactly the same data, but reading everything opposite, and that's the opposite category. And sometimes dualities turn things around, so that's why you need an opposite category. But just keep those constructions in mind. They're not super important, but they will appear from time to time. The point is that I would like to do is I would like to encode diagrams in Feynman diagrammatics or Penrose diagrammatics or just diagrammatics. So really a classical idea, a morphism. So I would just like to draw objects as points. We've already seen that. And I would like to draw morphisms as kind of coupons. Here's a morphism from, what is it, Y to X. So like a coupon. And associativity is just saying, for example, that this picture makes sense. Right? So this picture by definition is stack this diagram on top of this diagram and then stack this diagram. So you first have your F diagram, which as I said is just a box, and the composition is just stack another one on top, G, and then you stack an H on top. And this is just the same as doing it the other way around. So if you would bracket it like this, and the composition diagram is just this. It's just a string of a coupon, a coupon, a coupon. And now my strings are labeled by objects. So this might be a bit confusing. Upsala. I'm really bad at doing this. So because it's a Poincare dual, it's a much better way of doing it instead of this graph thing, which is really classical. So think of categories as graphs is really classical, and kind of the main idea to make it more fit to physics of people like Feynman and Penrose is to kind of take the Poincare dual. So in the classical picture, objects are one-dimensional, zero-dimensional, and morphisms are. So this is a classical picture, x and y. And if you take the Poincare dual of this whole thing, blop, blop, then what you would do is you would draw objects one-dimensional. And I mean, this is a huge thing, a huge coupon. And I just need a huge coupon because I want to write f. What I could also write is just a point, of course, labeled f. And then it's really just a Poincare dual picture. And it has some nicer features. That's why I will use it. It's called the Feynman calculus. And basically, what I will do is I will just use these diagrams. There could be some. We're not there yet, and you will see later. You can just stack them together, and you can just draw them basically as you want, and the axioms will tell you that everything's fine. So basically, two diagrams are equivalent if they're equivalent up to scaling. So it doesn't matter if I draw it like G H, or if I draw it like G H, very small, I can't even read it anymore, or whatever. And by definition, this is just HG, and so on. And I'm even lazy here and not labeling the strings anymore, which are objects now. So this is a bit confusing, so let me say it again. It's Poincare dual to the classical calculus. It's in some sense a much better one. Now the strings are labeled by objects, and kind of the boxes are labeled by morphisms. Okay, this is called Feynman diagrammatics. It will be extremely nice. You will see it. It will be great for more if categories have more structure. This will be super handsome. It will explain the whole terminology. For now, it's just a way of encoding well, morphisms and compositions of morphisms. Using the usual rule that identities are not drawn. So instead of writing a box labeled identity, I just write a strand labeled X. So this is a bit, by the way, if you read this is a bit of it's easier to illustrate those diagrams using Dix than those diagrams. But actually, this is just meaning the strand is labeled X. So strands are really labeled by objects. Okay. And the graphical calculus is consistent. And the only thing you need to check, so the two morphisms are equal if and only if the diagrams are related by scaling. And you can see it here. So if I have a morphism F, that's basically the only thing you need to check. And I compose it with an identity morphism. And it's just, so F goes from, let's say, X to Y, and I compose it with an identity morphism on Y, then up to rescaling, this is just my F itself. So nothing really fancy is happening here. It's just a reading convention that makes my life a bit easier. Okay. And this will turn out to be really useful as soon as we have something two-dimensional. At this point, it's just a one-dimensional thing. A category is a one-dimensional thing. A category is a graph. And there's not much you can do. It's a line, right? You can put labels on a line. Basically, what I said is it doesn't matter where I put my labels, at least as long as the order is preserved. Then it doesn't matter where I put my labels. It will be extremely handy as soon as we go to two-dimensional calculus. Okay, there is something that is called a functor. And a functor is nothing scary. A functor is just, okay, if I have a set, I have a map between sets. Now I have a category and I want to have a map between categories. And that's a functor. So if I have a category, so let's see, here's my category C, and here's my category D, and there will be some objects in my category A, B, and there will be some morphisms in my category. And all the functor is doing is it should send structure to structure. So it takes an X and sends it, let's say, to A. So F of X, F is my functor, equals A. And it takes a morphism, whatever, this one, call it F, and it sends it over to a morphism, call it G. F of F equals G. Okay, and yeah, what can I say? It's all built such that, so a map between sets is just a map. A map between vector spaces, well, you can use maps, but they're not really useful. You would use linear maps. A map between groups, well, you could use maps. They won't be very useful. So you would use group homomorphism, something that preserves the structure. And that's exactly what a functor is. A functor is just a map between categories. So to each object, you associate an object. To each morphism, you associate a morphism such that, source and target are sent to the right things. And what could you impose on such a functor? Should it be something random? No, there are two things in your category that you can do. You can compose things and you have identities, and both should be preserved. That's it. And functor is nothing scary. It's just a map between categories. The easy example is the identity functor, which sends everything to itself. Okay. Point is that it's structure preserving, right? Always keep in mind when if you have a vector space and you have a linear map between vector spaces, a matrix, and you compose it with another linear map, another matrix, what you will get is a linear map, another matrix. So matrix times matrix is matrix. Functor times functor, which I denote by just this symbol. First F, then G is again a functor. In particular, the prototypical example of a category, from my point of view, is actually cut itself. So categories are objects, C, D, E, and functors are morphisms, F, G, GF. I've done absolutely nothing, right? So basically nothing. I just added morphisms between categories. Keep in mind that the point of this whole thing is that morphisms matter, objects don't. So the first thing I should do is I should add morphisms between categories. Here we go, morphisms between categories. They really generalize a lot of familiar things, like maps between monoids. Just read those examples more carefully when you, as I said, everything is linked down in the description. And yeah, and I will also upload what I just write here on my screen. So all this blue, red, and whatever stuff will be an extra file. So really, functors generalize a lot of things. Let's do another easy functor. There's a functor that just forgets structure. So for example, a vector space is a set with a structure. Well, you can just send it to, and a linear map is a map with the structure. You can just forget it, and you get a forgetful functor, for example. Yeah. And yes, so very crucial examples of functors are home functors. They are a little bit complicated if you see it for the first time. They're not so scary. They're just the following idea. Pick an object, X, in your category, then by definition, whenever I put something in here, let's say a Y, this is a set, right? So this one. So I can define a functor from C to Z, from any C to Z, by just using the home functor. And composition is break composition, or do it the other way around. And here comes this opposite category. So I hope I did this correct in the lecture notes. It's always very confusing. So it depends whether you leave your blank spot, your placeholder in the second entry or in the first entry, whether you need to reverse the composition rule. But basically, you have home functors, which basically are saying like they are like maybe you know this classical gold foil experiment where you shoot electrons on the gold foil and then they split off. You should think of your X as being this gold foil, and you kind of shoot particles through this gold foil and try to see what's going on by looking at the uh, uh, outcome of the whatever kind of screen it is. I'm not a physicist, right? But that's the outcome of the screen. So where the electrons are. This is like the home functor construction. You choose some element X, and home is like you now you now shoot kind of objects at your chosen favorite object X, and you see what's going on, what the set is doing. And we'll see something like that in a second. Well, maybe not in a second, but at the end of the lecture. Anyways, they look very scary. Home functors, they're a pretty easy idea. Just fix your favorite object and consider this one, which is a set. So all maps that start at X and go somewhere. Yes, so let me also discuss maps between categories. Well, we could go on forever, right? Now, I told you about categories, they have object isomorphism. I told you about functors, they are maps between categories. And now I tell you about maps between categories. Yes, you can talk about maps between functors, and they are called natural transformations. And they do exactly what you think they are. There should be maps between functors. So ignore the abstract definition. You can read it. Basically, everything is built such that there is now a nice category, namely the category of functors, and that denoted by home CD. It's a category of functors from C to D, and the objects are now categories. So the objects are now functors, F, G, and the morphisms are those natural transformations. And what could those, you could already see that natural transformations have a two-dimensional calculus. I will explain that later. But basically, what's going on is alpha and I sometimes draw this with a double arrow. So here, alpha from F to G. And basically what this means is, well, what is a functor, right? A functor has some value on some X, and it has some value on some Y, and it has some F of X. That's my bottom line here, and you have the same for G at the top. So natural transformation is then just a collection of morphisms for each object such that this diagram commutes. That sounds a little bit scary. If you think about it, it's exactly what you want to do in order to have a category of functors, a functor category. And a very important special case is the endomorphism functors of a category. So all endomorphism functors of some category. Yeah, it's just home from C to C. It's like saying you have an algebra, and what you really want to consider is homes between algebras. Okay, but if you take endomorphisms of an algebra, which commute with the action of the algebra, then you get another algebra. That's basically what I'm saying. Those category of endofunctors will really play an important role. They're like symmetries of the category itself. We will see more about that not yet, not well later. But basically, I give some examples here. Um, so above, I explained, I skipped over it in this video, but above I explained how basically functors generalize actions and natural generation generalize intertwiners, which are really just AKA maps of representations. And if you look at this example, I hope it will make sense. Um, for now, that's not so important. So let's just wrap up. So what I'm going to explain next is some things we need later. And really don't be, ooh, this was really, really bad. So let me just do it this way. Later, it gets much better. As soon as you have more structure, it gets much better. But now it gets a bit technical. So let me wrap up by going through what we have seen so far once more. So a category is just this one-dimensional object, this collections of objects and morphisms that behaves like a graph, right? So it's kind of a discrete object. It's not really a discrete object. Well, the category of sets is certainly not a discrete object. There are quite a few sets, but it's no harm to think of it like a discrete object, a set of objects like a graph. And you basically have three main examples I want you to keep in mind. The real discrete categories, like this one or this one. This is the classical categories: sets, vector spaces, finite dimensional vector spaces, something like that. And these topological examples is really, really nice. So just boundary points are just points, certain number of points. Objects are just certain number of points. And morphisms are basically everything you can draw in between to connect those points. Composition is stacking, and strictly speaking, rescaling. And there are various flavors, and some of them get really topological. Get topological. Like this already looks like something that is kind of tangled in three space, and this looks like something that, well, it looks like something that is tangled in three space with orientation, but you should think of it like a particle traveling through time and space. Then we had seen those Penrose diagrams, which will play an important role in my lecture anyway. So just boxes and composition of boxes in the way that it makes sense. And this is a really nice drawing because I just try to fit it on the page. And actually, the point is, it doesn't really matter how I draw it, as long as it's a one-dimensional thing. As long as I keep the order, I'm fine. Which is the strict formulations in this theorem. Okay, and then I discussed briefly maps between categories. They're called functors. So what are functors supposed to do? They're supposed to assign to each object an object and to each morphism such that the natural rules of categories are preserved. And the prototypical example, you should keep in mind that everything is built such that the category of categories, is a category. So compositions of functors. It's a functor, there's an identity functor, you know. And they generalize a lot of notions that you've seen before. The home functor maps between categories, natural transformations. Well, what is it? Well, a functor is basically this datum, right? A functor basically to each thing like this, and the category assigns this picture. So G does the same here. So a natural transformation. I can't speak today. Why? A natural transformation is just an assignment between those pictures, and the only thing you can come up with is a map for each x, and a map for each x, so also for each y, right? Such that this diagram computes, and that's the natural transformation. Strictly speaking, it's a collection of morphisms for each x, such that this diagram computes, and this is called naturality. That's why it's called a natural transformation. Don't ask me who came up with this terminology. That's a pretty stupid terminology. In particular, in mathematics, you always run into the trouble that you want to say, oh, this is a natural construction, in the sense of, I think it's natural. But then you run into the trouble that there's a mathematical term, naturality, and you don't mean that, and it's horrible. But anyway, it's called natural. We can't change the rules, right? It was probably coined by Eilenbach and MacLean. Yes, I'm pretty sure. I'm pretty sure. But anyway, it might not be a very nice terminology. I don't want to blame them. Anyway, so naturality. It's just meaning that this diagram commutes, and commutes, remember, just means that both compositions give the same result. Very good. And the point is you can stack them on top of each other and you get something like it's called a vertical composition. And I call it a vertical composition because I just take this diagram and it's the bottom here. I take another one for another functor h here at the top, and I stack them together. That's called vertical. Vertical. Okay, and everything is built that is an identity natural transformation, and composition of natural transformation is the natural transformation. So you have categories of functors which are denoted by home or end. Very good. Some notions we will need. Well, I just go through it very quickly, and then I will come to an end. So an isomorphism is just an invertible element in your category. So you have the existed the G, and the G is of course the inverse, right? As usual yoga, this G is unique, so a G is F inverse. So G equals F inverse. This is like in vector spaces. This is a bijection. Bijection is invertible, and all the invertible elements are bijections. And the monomorphism is kind of the categorical analog of an injection. It's also called monic. If you can cancel, you can't write injection. You can't write it's injective because in general these are not maps. So here's the right analog. You say it's an injection if you, well, sorry, it's monic. It's a monomorphism if you can cancel it from the left, which just means if you have something like this, then you can cross this out. And there's a dual notion, which is called an epimorphism or epic, a surjection, without mentioning the terminology surjection. And it just says if you have something like this, then you can just cancel it from the right. And the point is, an isomorphism is always monic and epic. The converse is not true. So iso implies monic and epic. In particular, isomorphisms, you can always cancel them from left or from right. They're really like units. It's like invertible elements. You don't really care so much about isomorphisms in some sense. And of course, F is just the inverse. And I really want to keep you in mind that in a lot of categories, these notions are just bijection, injection, surjection. B in, or maybe I should call it B. maybe I should call it bi. Bijection, injection, surjection. But not always. Right? So this funny example, all morphisms are monic and epic, but none of them is an isomorphism. And injective and surjective even doesn't make sense. But again, as an analogy, this is perfectly fine. And now you can say, well, two objects are isomorphic if there exists an isomorphism. And you can play a similar game with sub-objects. If the sub-object is something that is the monic morphism, a quotient is something that is the epic morphism, and the sub-quotient, blah, 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 blah. Okay, but basically the main notion here to take away is you can use this to define certain relations on objects. Two objects are isomorphic, two objects are eine sub-object configuration, I don't know what to call it, some My drawing skills are so horrible. Some objects are in a quotient configuration, depending whether you have isomorphisms, monic morphisms, or epimorphisms. Yes. So this is really important. So let me stress this. That you might have things that look very different, like Z mod 4 and Z mod 2 cross Z mod 2. But in subcategories, they might be isomorphic. They're isomorphic in set, because isomorphisms in set are just bijections, and both sets have 4 objects. But they're not isomorphic in something like abelian groups, because they're not equivalent to abelian groups. So what equivalence and what isomorphism means depends on your parent category, depends on your chosen universe. Your category is your universe. You're sitting in your universe, and your universe determines what is epic, what is monic, what is an iso. So you can't distinguish those two things in set, but you can distinguish it. You can distinguish them in what? In abelian groups. Yes, and of course, you then get the notion of categories being isomorphic, just meaning that there's an isomorphism of there's a functor which is an isomorphism in the category of functors. Okay. And well, if you already have the notion of a sub-object, then you can define the notion of a subcategory. So let me run you through it, because it's kind of the thing I want to wrap up with. By the way, I'm always writing more in the lecture notes that I'm going really to discuss in the lectures. So I encourage you to read the lecture notes. They're not perfect. If you find mistakes, if you have questions, let me know in the comments, or just write me an email, whatever, and I will correct the lecture notes. But I'm skipping a lot of things here, as you can see. Just so I don't know how you feel, but after listening for 1 hour to a lecture, or for 1.5 hours to a lecture, I'm just super tired. So idea is just, well, let's just, this in my lecture, I will just try to tell you the bigger picture. And I hope to just, well, for the details you would look in, or details and more examples you would look into the lecture notes. And not just in the lecture notes, also there's a lot of literature, of course, which I cite at the end of the lecture notes. Anyway, this was a distraction. So subcategory is a subcategory. So we have, what is a category? A category is objects. So a subcategory has, well, the objects are formed a subset of the other objects, and the home spaces are formed a subset of the other home spaces. And for the home spaces, you really need to be careful that this is in C and this is in D. So for instance, finite dimensional vector spaces is a subcategory of vector, because I take a subset of the objects. I just take finite dimensional vector spaces. I would call it dense if basically if this is equal up to isomorphism. So for each y there exists an x that's isomorphic, and I would call it full. So this subcategory, this might be a huge difference here, and I would call it full if the home spaces are equal. For example, this is full because all linear maps between finite dimensional vector spaces are all finite, given by looking at the basis elements, right? So they're matrices. And it doesn't matter whether I'm in vect or I'm in vect or a finite dimensional vect, but certainly this is not dense, because there are certainly infinite dimensional vector spaces which are not isomorphic to finite dimensional vector spaces. They can't be, right? Finite dimensional vector spaces are finite dimensional. Very good. So yes, we will discuss group classes later. So for now, it's not so important. You basically, what you do is you have this notion up to isomorphism, and the usual philosophy would be, well, let's ignore that for now. Let's say those are equal, and you basically mod out by this relation. And what you would get is what is called a skeleton. This is just identify isomorphism classes and just call them a new object. It's a classical strategy. Um, yes. So the skeleton, for example, of finite dimensional vector spaces is really matrices. And matrices is just a very naive category. Objects are natural numbers, and morphisms are, oh shit, matrices, M times N matrices, I hope, or the other way around, nobody knows. But it's like okay, vector spaces are up to isomorphism given by choosing a basis, and if I ignore, if I collapse equivalence class, it's like choosing a basis. So I can just talk about matrices, and the Grothendieck classes are really just the equivalence classes of objects. Right? For a vector space, I only care about that. I care about its dimension. For let's say finite dimensional vector space. If I get all the other information in vector spaces. Okay, so here's, for example, K0 of finite dimensional vector spaces. And how does the map work? Well, the only information hidden in the equivalence class of an n-dimensional vector space is actually the dimension. So you just, the equivalent, the morphism here is just sending a vector space to its dimension. So V to dim V. So this is a huge loss of information, but still it tells you something about your category. So that's why it's important. It's called Grothendieck classes, later Grothendieck groups or Grothendieck rings. We'll see more about that later. Yes. And the main notion I want to stop with, and we'll come back to more Feynman diagrams later, but this is kind of the main notion I almost want to stop with. I will run you through the rest very quickly, is that two categories are equivalent. You always see it, you always see it here. So these two categories are basically have the same information, but they're not isomorphic. Why? Because this has way more objects. This is infinitely many objects, and this has just one object per dimension. Because you collapsed everything, they can't be isomorphic. Isomorphism would ask for a bijection on objects. This is just never going to happen. So the right notion in category theory is a notion of equivalence. Two categories are equivalent, not two categories are isomorphic. And here's the definition. It's exactly the same, but you only require that F is invertible up to isomorphism, G is invertible up to isomorphism. Don't look too much on the abstract definition here. We will see more about it, but the point is they are equivalent but not isomorphic. Okay? So equivalence is the right notion. Equivalence preserves everything basically you care about in categories. Relations, namely morphisms, namely morphism spaces. You don't care so much about objects. It's not really important whether I have 5 objects which are all equivalent or just collapse into one. As long as home spaces have the right size, you are happy. And this is just captured by, I give you some more examples. This one is a nice one. I will come back to this in a second. But just captured by the following proposition, which I really would like to keep. This is not the definition of equivalence, but you can take it as a definition if you want. It's easier to remember. So two factors, a factor is an equivalence if it's basically fully faithful and essentially dense. And this just means the following. And then two categories are equivalent if there is an equivalent, such an equivalent factor which is equivalent. So what is dense? Okay, so this is really the crucial part. Faithful means it's injective on home spaces, and full means it's surjective on home spaces. So it's a bijection on home space. It's all you care for in categories. You don't care about objects. That's why here the right notion is dense. So it's not a bijection of objects, but it's a bijection up to equivalence. So this is bijection up to equivalence. right? And this is really a bijection. Ooh. Ooh. This is really a bijection. Very good. The rest is not so important. There will be a Joneda lemma, which I will just mention. So let me just mention the Joneda lemma, and let me just finish with this funny example. So have a look at the Joneda lemma, which is kind of the best thing you can prove about general categories. It's basically saying that a category is given by the gold foil experiment. The category is they are fully faithful functors, so equivalences up to objects, and C is always equivalent to some home category. Well, not equivalent, but it's fully faithful. So all the important information is preserved, and depending in a bit in which direction you want to do it, it's really the best. So this is called the Unida lemma, Unida functor, whatever. It's kind of the best thing you can prove about categories. Categories are determined by the functors to sets. That's basically what it's saying. Categories are determined by some kind of gold foil experiment. You take your home functor, and everything that goes through this gold foil is determined by your x, and all the maps are kind of determined by the home functor. It's not super important to keep it in mind. I would like you to read it, but yeah, it's just a really helpful. Well, I wouldn't call it a technical result, but it's a very helpful result. So yeah. So this is basically what it is. For any functor f and any x, there's a bijection of this set, basically. So basically what it's saying is this is a consequence of Unida embedding. You can embed C into a category of factors. So any C is of the form, well, this is just not quite true. It's a subcategory, but anyway, is of the form home C to set. And maybe I should put it up somewhere here, but whatever. So you can always embed, so all the functors from your category already know everything about your category. That's what I say. Okay, I hope you will do some of the exercises. This is a crazy diagram. You can check that it's commutative. I hope you will do some of the exercises. Exercises at the end of each section, chapter, whatever you want to call it. But let me finish by discussing this example because it's a lot of fun. So let's take the category of finite sets. So finite sets up to bijection. Okay. No, sorry. It's a category of finite sets with only bijections. Oh, I can't write. I really can't write. Only is a very hard word, right? Only is a very hard word. With only bijections. But for instance, there won't be a map between size 3, a set of size 3 and a set of size 4. There can't be a bijection between them. But there are quite a few maps between sets of size 4. How many? 4 factorial. Well, how do I know? Well, because I claim this category is equivalent to the category which I call symtop, which is a subcategory of my one-dimensional cobordisms with only cobordisms with cobordisms without Morse points. So you don't have some things like this. This is a Morse point. So you never change height. You only go in one direction. So a typical diagram is something like this. And why is that true? Well, because this is really just a permutation diagram. So let's just think about it. You have a certain number of points at the bottom, let's say 5, and you only care about bijections. So you certainly only have the same number of objects at the top. And if you give those things names, 1, 2, 3, 4, 5, you can think of this as a set. Oh, yeah, 1, 2, 3, 5. They're very good. 1, 2, 3, 4, 5. You can think of it as a set with 5 elements. And each diagram you now draw like this without, so just connect 2 points. Here you go. Just connect 2 points without changing height. Whatever, this one. Maybe like, ooh, this was really bad. Maybe like this. Maybe like this. Defines your permutation. So let's see. So this is just a permutation. 1 goes to 2. Very good. 2 goes to 5, as far as I can see. Yeah, very good. 3 goes to 1. 4 goes to 3. Oh, very good. And 5 goes to 4. So all of these diagrams define you define you a permutation. And the right relation on those diagrams are the so-called Reidemeister moves. We will see more of them. So whenever you're very lazy to draw a diagram like this, so 1, 2, 1, 2, then this is of course the same permutation as you have done nothing. And then there was this funny choice of, I don't want any triple points. I don't want to draw this diagram, right? I kind of don't want it. And there are 2 ways to resolve this issue. You can pull this string, this was bad, to the left, or you can pull this string to the right. And the last relation is saying that these are the same. So let's check. So here 1 goes to 3. Here 1 goes to 3. Very good. 2 goes to 2. Aha. 2 goes to 2. Very good. And 3 goes to 1. 3 goes to 1. Ah, yeah. Very good. So it really is the same permutation. And the magic is that these 2 are the defining relations. Of permutations and as well of the subcategory of one-dimensional cobordisms without most points. So they really are just the same categories. And again, a nice diagrammatic interpretation of a category of a mathematical object, category, morphism, whatever set that you've seen before, permutations, just like string diagrams in the one dimension, in the cobordism sense. Okay, that's it for today. Next week, we'll see a little bit about 2-dimensional categories, which are called monoidal categories. But for now, I can just say I hope you enjoyed the lecture. If you have anything, as I said, everything will be linked down in the description, like the link to the lecture notes, the link to those notes, which I will update, of course, weekly. And depending when you see this lecture, this might be already completely updated, of course. And I really hope you enjoyed the lecture. You learned a little bit. I try, as you have seen in while I'm giving this lecture, I try to avoid all technicalities. I won't tell you about proofs or anything. You can read them in the file. There are a lot of other materials you can look up. ECNO is a really nice book. Standard books on category theory. The point of this lecture is to give you a feeling how to work with those things. I hope you enjoy this strategy of mine to try to explain something that looks very scary to people, like category theory and low-dimensional topology. Might not be too scary, but they're the same thing. That's what I want to explain anyway. Anyway, I'm already starting waffling here. So that's it for today. Hope you enjoyed the lecture, and just let me know, right? In the comments, write me an email or whatever. And I see you next time.